Hello students, welcome to Physics 1200 Unit 1 Lesson 2. In this lesson we're going to be looking at heat, thermal energy, and internal energy and specific heat. So the objectives for the lesson, for this lesson we'll define internal energy, define heat, explain the units for heat, and we'll relate heat and temperature change. Internal energy, as you can see in the diagram, we have a visual depiction of molecules, and these arrows represent the motion of the molecule, maybe bouncing off the side of the box and moving on. So this type of motion of the molecule going and bouncing represents kinetic energy, just like a ball, being thrown, or anything with motion and mass results in kinetic energy. So we're talking about molecular kinetic energy. And we also talk about the molecular potential energy. All right, so there are other kinds of molecular energy that we're not going to get into in detail. Essentially, when we heat an object, we excite the molecules, and the molecules gain more kinetic and potential energy at that molecular level. So it's really important to be very clear on the difference between internal energy as a definition. It is referring directly to the energy. In other words, we're talking about the noun, the energy noun here. And temperature is a measure of energy, okay? So make sure you don't confuse the idea of temperature with thermal energy. And then we introduce another word to this, and that word is heat. Now, heat is the process. It's the flow of the thermal energy, okay? Be very careful to have these three definitions clear in your mind. We often in our questions phrase it as heat because the questions have to do with a transfer of heat, a reaching of equilibrium, a requirement of the need to heat up to a certain amount. So the word heat is the best word. It's like the action, it's the verb for the thermal energy, the flowing of. And in this diagram here we can see the gentleman in the yellow shirt holding on to a coffee mug. And of course, it's hot coffee. That's why we see the steam coming up. Therefore, there is going to be heat flow into the person's arm. Now, in the second diagram here, diagram B, we have a person holding a glass of ice water. So it's colder than the internal body temperature. That's about 36, 37 degrees Celsius. And therefore, the heat from the hand will be flowing out into the coffee cup. So that shows us the general rule of heat flow, which is from hot to cold. Okay. Since heat is the flow of energy, the units of heat are the same as those for energy itself. And we call that, of course, joules. So we have the symbol Q representing the thermal energy heat flow and the units of joules. So heat flows from hot to cold, and it originates in the internal energy of the hot substance. It's not correct to say that the substance contains heat. It contains what? It contains thermal energy, and heat is the flow. Okay, so just to recap, temperature is a measurement of thermal energy, which is the noun, the actual energy we're talking about, the molecular energy, and heat is the flow, the process, the action, the verb. Here's a visual depiction of heat flow from the warm body to the cold body in a very basic, type of diagram here. So we have heat flow from the hot moving down to the cold, okay, similar to the hand holding on to the coffee cup. Now that we've defined the difference between heat and thermal energy, let's look at three more objectives that are strongly connected to thermal energy and heat. Those are define specific heat capacity, explain the concept of calorimetry, and perform calculations based on calorimetry. So the specific heat capacity is a value that we call C, and it describes the amount of energy needed to raise the temperature of 1 kilogram of material by 1 degree Celsius. So if you take a look at the table here, we have various substances. For example, aluminum in a solid state has a specific heat capacity of 900. Now the units for specific heat capacity are joules per kilograms per degrees Celsius. Okay. You can think about specific heat also as the amount of thermal energy a particular material has the ability to hold. For example, water versus metal. We all have some familiarity based on using just stoves in the kitchen that it takes a long time to boil water, but it does not take a long time to heat metal when you have it on an element and it's empty. So if you put an empty frying pan on the stove and you heat it up, it gets hot really fast. If there's water in there, it takes a long time. So what's happening is the thermal energy goes into the metal. The metal doesn't take a lot of energy to raise its temperature. In other words, it doesn't hold a lot of heat. When it's hot and you cool it down, it only gives off a little heat. Versus water. Water takes a long time to heat, which means it absorbs a large amount of thermal energy. And when it's hot, we can say it's holding a lot of energy. What type of thermal energy? Okay, so there's a couple ways to try to wrap your head around the meaning of specific heat capacity. One of the ways that we explore this idea is to look at, well, A, our formula, and B, we'll look at calorimetry. So our formula for specific heat capacity is Q, the heat that we call thermal energy and the flow of it. We have M for mass, how much of the substance do you have, and C, which is the specific heat capacity, and then of course our measurement of this, the change in temperature. And remember, delta T is T2 minus T1. All right, that's a change in temperature. So, you know, we need more energy if we want to have a great change in temperature. So if we're going from 0 to 100 versus 0 to 10. And of course, mass has an impact too. If we're heating a lot, it takes more energy to do that versus heating a little bit. Okay, common units for specific heat capacity, again, we see them down here, joules per kilograms per degrees Celsius. Now, calorimetry is a concept where basically in the lab, we will be looking at identifying the C value of an unknown substance, this blob here in the water. So it builds on the concept of the conservation of energy right here, where the change in heat is balanced. In other words, if the water starts at a cool temperature or room temperature, let's say, the metal or the unknown substance we put into the water is very hot, all right? When we drop the hot metal into the water, the energy that's stored in the metal will be given to the cooler water. And at some point, they'll reach an equilibrium temperature. And if the conservation of energy stands, the energy donated equals the energy gained. Okay, so the energy loss equals the energy gained. Let's take a look at this in action. Let's take a look at a question here. In a half hour, 65 kilogram jogger can generate 8 times 10 to the 5 joules of heat. This heat is removed from the body by a variety of means, including the body's own temperature regulating mechanisms, things like sweating and whatnot, you know, the capillaries releasing energy from at the surface of the skin. So if the heat was not removed, let's just pretend you don't sweat and no heat's being given off, how much would the body's temperature increase? Well, if the amount of energy can be found by taking the mass times the specific heat capacity times the change in temperature, of course, if we're looking for the higher temperature, how much it goes up, we are looking for delta T. Okay, so that will give us a change in temperature will equal Q divided by MC. So we need to take the MC here and divide both sides by MC to isolate our delta T. Okay, so we get delta T equals Q divided by MC, then plugging in our values of energy here and the mass of the person here and the specific heat capacity for a person there, C, we get a change in temperature of 3.5 degrees Celsius. Let's take a look at a calorimetry problem. Now this is a little bit lengthy, but in essence what we have is a substance added to water and the aluminum can itself. So calorimetry is made, the calorimeter is made of 0.15 kilograms of aluminum, okay, and contains 0.2 kilograms of water. This will be what gains energy, the aluminum and the water. They have an initial temperature of 18, and then we have a mass of an unknown material 0.04 kilograms of it, and it has an initial temperature of 97 degrees Celsius. And we add it to the calorimeter. We wait, and it reaches thermal equilibrium. So this unknown metal has donated thermal energy to the water and the can. And what we need to do is find out the specific heat capacity C of the metal. Okay, it tells us right here that the final resting temperature for everything is 22 degrees Celsius. So let's kind of take a look at how we might solve this question. On this side of the equation, we will take the Q of aluminum and we add to it the Q of water, because they're the two objects that are gaining, okay? They gain thermal energy. And because the gain and the loss are equal, that means the Q of the unknown substance will be on our loss side. Okay, so in other words, Q gain equals Q loss, and on the Q gain side we have two things, the aluminum and the water. Now we know the values of everything here except this C value here. So let's see what that looks like. C unknown, this value here, okay, will basically equal this entire side divided by M over here divided by delta T there. So we have to do the same to both sides, and what we get is this expression. Take the mass and the specific heat capacity and the change in temperature of the things that we know and divide it by the mass and the change in temperature of the things that we don't know. So if we fill in all of our values here, now keep in mind there's a lot of numbers here. You have to be very careful with how you use your calculator. We're going to find an answer of 1,300 joules per kilogram per degree Celsius. It's often the task when we find an unknown C to identify, okay, identify the substance from a table. So we did have a table that we looked at before, and if you get a value in the lab, what you're going to have to do is you're going to have to take a best guess as to what it is you have, what type of metal it is that you have. Okay, that's it for today's lesson, everybody. What I would like for you to do now is take a look at some of the online materials I've posted for you to practice calorimetry, specific heat, and make sure you're clear on your definitions of temperature, thermal energy, and heat. Okay, thank you. Have a good day.